Now that we've defined speed and velocity, we can start connecting those to what we already had for position and time to represent in a bunch of different ways. Remember, we generally use x to represent the coordinate of an object, but that's really for left or right motion. We'll use y for motion up or down. And in chapter 2, it's not a big deal in this chapter, but in future chapters it will be good to keep those separate, so it's not bad to get it in your head now. Alright, we can represent position on a motion diagram, as we did earlier in the class. Every dot represents student position at a particular time. Alright, how could we produce the motion that's on this diagram? Well, we could say that they move at what seems to be kind of steady motion here, that every flash they move about the same amount, but then they slow down quite a bit, and then they speed up again, probably even faster here than they were early here. All right, here we've got a position time graph, or a time series of the position information, and we can show the dots in the same place. But what we've done is we've moved them, sort of laid them out and put the positions on the vertical, and we can see that now the object's positions are marked here. Keep in mind that the object is not traveling along this dash in any physical sense. It is on this graph, but it's not actually moving at sort of this angle and going up and stuff like that. It's just moving over, in this case, uniformly towards the positive. All right, consider the slope of the graph. Slope is defined as rise over run on any graph. All right, and the rise is the change in the vertical coordinate, or the run is the change in the horizontal coordinate. But in our graph, change, of course, is delta, and our vertical coordinate is x, and our horizontal coordinate is t. So rise becomes delta x, and run becomes delta t. Therefore, the slope on this position graph is delta x over delta t. But that's just what we define velocity as, the average velocity. So we see that on this kind of graph, we get that the slope on this kind of graph is the velocity. All right? Keep in mind, it's on an xt graph. That's emphasized down here as well. We'll have lots of slopes in the class. They'll mean different things based on what kind of graph you have. The axes determine what the physical interpretation of the slope. All right, here's a motion diagram of a car moving along a straight road. What position versus time graph could match this motion diagram? We see that there's less distance during these intervals than there are during these intervals, and that the change happens just as it passes the origin. Right? The origin is going to be where x equals 0, which is the t-axis. So it should be a change in speed when we get to the t-axis, where it is going slow and then going fast. And slow would be low slope, and fast would be high slope. So we're really looking at this one. What distinguishes D from E, which look like the same graph? D says that at t equals 0, we're at the origin. But for r t equals 0, we're not at the origin, we're left of it. So we need to start with a negative value. So it had to be either B, C, or E. C has a constant slope, so that's constant velocity, so the distances would have to be the same, so that one is out. And B has the faster thing and then the slower thing, so that one's out as well. All right, here's a motion diagram of a car moving along a straight road. Which velocity versus time graph matches this motion diagram? So now it's a velocity versus time graph. Right. Not surprisingly, maybe you can see that this is the same graph, same motion as before. And again, we said that there was basically something was traveling slow here and faster here. In both cases, heading towards the right, so they're both positive. So we look for something that has only positive values. Oh, they all have only positive values. And we expect there's a moment right here where they suddenly abruptly change speed. But before and after, the speed seems to be constant, so that would be C. All right, finally, a different kind of motion. Here's a motion diagram of a car moving along a straight road. Which velocity versus time graph would match this motion diagram? So, a couple important things. We can see that the thing is always moving to the left, which means the velocity is solely negative. Right? It's always against the direction here. So we can throw out this one, and we throw out this one, and we can throw out that one. And then we want to say, well, we're moving to the left, so we start far to the negative, 4 in the positive region, but we start moving leftward, and we're over here. We can see that this region is slower, and then it gets faster. But it's negative, so we have to be careful. Slower means a smaller magnitude in speed, not a lower velocity, but a lower speed, which means closer to the axis. So we should start off with a low velocity in magnitude and pop bigger, and we can see that that is this one. All right, a graph of position versus time for a basketball player moving down the court appears as follows, and is given. Which of the following velocity graphs would match the position graph that we showed? What jumps out to me, at least, is that during this first time, it has a velocity of 0. The position isn't changing at all, so its speed should be 0. Put a different way, it's got a slope, but it's horizontal, so the slope is 0. So in all cases, we're looking for a velocity that has an initial 0 part. And so we can throw out that. The others all have initial 0 parts. And then we see that it becomes a line. The line has a negative slope, but is otherwise, it's a line, so it's constant. So we need to have the velocity should be constant. That throws out this one. And it should be negative, so it throws out that one. And we're left by elimination that it must be C. All right, draw the velocity plot that corresponds to the position plot above. We see that, again, my eye immediately goes to the x is constant between 2 and 4 seconds, so that's going to be a velocity that is 0 between 2 and 4 seconds. So I'm going to jump right with that. And then prior to that, we have here a slope that is negative, and it looks like it's got a slope of, actually, let's do a color. Let's take over here. We're going to say V in that region is delta x over delta t, slope of that line. So it looks like we end it at minus 4 meters starting at the origin, and we end it at 2 seconds starting from 0 seconds. So this is minus 2 meters per second. And then it jumps up to here, sort of aphysically. And then over here, on the right hand, we're going to take a slope anywhere in here. Are there easy places? Sure, I'm going to take the whole triangle. This is a difference of 10 meters over 2 seconds, which is 5 meters per second. So it jumps up to here until it runs out. And again, somewhat aphysical instantaneous jump. This, you should be wary of. These sharp corners lead to sharp cliffs. These are sort of non-physical. Really, objects can't abruptly change their speed. So there really should be some little rollover here. It should go like this and then roll over smoothly, which means the velocity plot would sort of have a little curve in it. And all we're saying here is that that happens over a short enough time span that it doesn't show up on our axes, that our resolution is too coarse to see that change. But it can't really instantaneously jump that way. All right, so here's our graph. It says, now briefly describe the physical motion of the car from 0 to 6 seconds. Well, we know that for the first 2 seconds, the car is heading, let's say, leftward at 2 meters per second at a constant rate, and then it brakes and stops for 2 seconds, and then it reverses direction, so it's going the other way, and it's going more than twice as fast, it's going 5 meters per second the other way. We can go from a velocity plot to a corresponding position plot with the warning that this is only really simple to do when the velocity is a series of constant values. So when the velocity is a bunch of horizontal segments, then we can easily produce the position plot. If the velocity plot is something other than horizontal segments, then we can still do this, but we're wandering into calculus. And we'll talk more about how we can do that in a shorthand, and then defer doing it formally till you take calculus in a math class. If we look over here how this works, of course, if we have a horizontal line at 1 meter per second, then we should have a slope of 1 for the first 15 seconds, which gets us from 0 to 15. And then we jump down, and we're going minus 3 the other way, so we have the line going with 3 times the slope but going the other way, and we construct it that way. All right, a graph of velocity versus time for a hockey puck shot into a goal appears as follows. Which of the following position graphs matches that velocity graph? My eye is again immediately drawn to this section where there is 0 velocity, which means we should have a horizontal position curve. And only 2 of them have that, so this is no good, and this is no good because those are not... oh, I lied. Let's take that back. A actually does have a horizontal at the end. And then before that, we have a horizontal velocity, so we should have a linearly increasing position. So it could not be A in that case. And then we shouldn't have instantaneous jumps in position because it just stops moving at this location. It doesn't teleport, and that throws this one out. So we end up with this one. Which velocity versus time graph would go with this position graph? Here we want to say, well, at the start, in this region, it looks kind of linear. And so, right, it looks a bit like a line. So I'm looking for a velocity that starts off looking kind of constant. But in this region, it looks like it's gone horizontal. So the velocity should be 0. So we should have something which is positive and then kind of gradually becomes 0. This doesn't start off as positive. This doesn't start off as positive. We need it to be constant in the early region. That throws that out. And so we're left with this as our possibility. Constant velocity rolling over to a decrease during this region is sort of here, and then it becomes 0.